Good morning, everyone, and welcome back to the next course in Business Digital Architecture courses. Today, video is about AI and big data. Um, in this course, I will try to present in general the different aspects in artificial intelligence. We'll start with fundamentals, machine learning, deep learning, computer vision, some information about natural language processing, GenAI, LLMs, and about the architecture behind the AI. Of course, how to deploy our models and some rules for, of course, responsible AI, and at the end, a quick overview about big data. So let's start with the history of AI. As you know, AI is not a technology that just show up. It's just, actually started in 1936 by a guy called Turing. And in 1950, he created a Turing test to evaluate how machines uh, behave and ability to exhibit intelligence. And the problem why we took so much time from 1936 to 2026 is like 100 years to have something like ChatGPT is like we got many AI winters during this period, and because of mm, um, problems in like hardwares was not efficient. As you can see here, the first winter was like a period of reduced funding and interest in AI due to unmet expectations of the early 1970. After we got expert E systems, just after a second AI winter, and as you know, we got in 1997 Deep Blue, like the first system that can be described like intelligence, and that beats the world championships, the Mr. Gary Kimovich Kasparov. There is a famous series about this event called Rematch. It's like a series created in 2024, if I remember, and it was really realistic. It shows how AI actually start from basic algorithms like brute force to more complex ones using strategies and learning, of course, abilities. So this is the quick overview about the history of AI. Of course, we got some more interesting events after, for example, in 2017, Alphabet or Google created AlphaGo, like the first agent to beat the world champion in Go game. And as you know, in 2023, we got ChatGPT 3, and now everyone uses LLMs since then. So let's talk about what are key, the fundamental case about artificial intelligence. Um, a simple definition of AI is like the science of making machines do things that require intelligence if it's done by a human being. And for example, understanding languages, making decisions, learning from experience. This is like require a real intelligence, and of course recognizing images. And in our daily life, We use AI in those examples like voice assistants, run your Siri or Alexa, Netflix movie recommendation, spam email filters, self-driving cars, etc. And here is a small diagram that shows the how like artificial intelligence uh, combine like machine learning and deep learning, and also now we have like generative AIs, and of course natural language processing. So as you can see, GenAI is a subset of deep learning, and its own a subset of machine learning, and so on. NLP is like the aspect that take a part of artificial intelligence and at the same time deep learning and machine learning. And we will discuss this later more in details. So about data fundamentals, mm, as you can as you can see, like data is the most important part in um, an AI architecture. It's like the oil of all that mechanism. Imagine you have like a car or don't know, submarines, aircrafts, planes, but you can not use them because you don't have oil, so they are totally useless. So even if we got the algorithms, powerful algorithms, powerful and very structured uh, architectures, we cannot like use them without um, accurate data. So data is very important, and it's like the most if it's like the most important part, really the most important part in any models, any LLMs, any system of prediction or of the generation. So how can we get data? We have like many ways, like we can use sensors. For example, your smartwatch can be a device to collect data. We can use database, for example, in banks. We have a lot of data about our customers. It's structured data. We will talk about that later. User interactions, for example, if you're using social media apps, um, uh, your interaction with the app can be collected, how you interact can be collected and use it later to suggest videos or, for example, for advertisements or something like that. And we have images and videos, of course, text documents, etc. We have like three type of data: structured one or relational data. It's the data organized in tables. We have columns and rows, and you can get any information just by using the primary key. We have a lot of relational database management system like Oracle, MySQL, PostgreSQL also, etc. And we have unstructured data like text, images, videos, audios, etc. And at the end, semi-structured data is like data collected and stored in format like JSON, XML. It's structured, but like it still have like a non-structured part, but you can still like detect the patterns in those files. And as I said before, like high quality AI systems require actually a real, a very good data, and also a data that is accurate and relevant, and of course a lot of data. As you can see, large volumes of data. Poor data quality leads to inaccurate models and biased predictions. So it is really important to pay attention to this point because without inaccurate data and a data that like shows the context of what are we trying to do with our models, we cannot have like something functional or something useful. So this is very important. So about like the machine learning overview, um, as I said, it's a subset of AI that allows computers to learn from data without explicit programming. And the main workflow used in many different machine learning models, we have the part of data collection, data processing. Here we are talking about future engineering, like chosen futures like that we will use in our model, um, deleting some rows like where we don't have values, normalize numerical data or features, um, create two categories, for example, numerical features and categorical features. And this is like a whole part, and we have like engineers that like specialize just in feature selection and the feature engineering in general. And after we get clean data that we can put in our model, we can try to train it using some algorithms. Like if it's a model of classification, we can use random forest classifier. If it's like a model to predict price of something, we can use linear regression models or algorithms, etc. And after training, of course, we will have some inputs that we need to evaluate if it's good or not. And we have like many different metrics. For example, in classification, we have accuracy, if one, recall, precision, etc. And for linear regression, we have um, like the ways to minimize the error, like for example, the gradient descent, and so on. After the model evaluation, if it's like okay, we can go to deployment and we can retrain if needed. So the basic idea here is like instead of writing rules manually, like as we do before in programs, we train models using data so they can discover patterns and make predictions. Example like where we use machine learning, we have email spam detection, protection recommendation, fraud detection, etc. So let's dive deep in this field. And before, just a quick sum up about AI, um, we have two parts like AI general intelligence or strong AI. Um, we don't have this type of AI yet, and like we're still working on it. It's like a general AI that like has the all the uh, knowledge created by the human being. It's like a super AI that understands and can do anything, not like a one human being can do, but all the human beings combines can do. So it's like mm, it can be like a science fiction, but for me it's like very um, achievable, and just we need more um, powerful hardwares and more complex architectures to do that. But we're still working on it, and we don't really have something that like look like the strong AI now. And we have the narrow AI or the weak AI. It's like the AI you use every day, and it's divided in two parts. We have predictive AI, It's like AI that predicts, don't know, prices, weather, something that look like that, and generative AI like LLMs to create text, image generation, audio like Sona, and video generation, of course. So machine learning has like three categories: supervised learning, unsupervised learning, and reinforcement learning. Let's start with the supervised parts. Supervised learning is a machine um, learning approach where the model learns from labeled data. This is the important part. The goal is to learn a function that maps input to outputs. So we have x's and y, and we need to find the weights or like the parameters used and can be used to map the x's to y's. So we always have the labels for each x. I already present some example of this aspect, but like the main idea here is like in classic programming, we have rules, data, and answer. For example, rules can be a mathematical formula. For example, B equal A multiplied by um, like Y equals like A multiplied by X plus B. Here, data is X, rules are A and B, and the answer, of course, is Y. In machine learning, it's completely different. We have Y's, answers, Y's, and data, which is X's, and what are we looking for is the parameters, the A and B, so like rules. And we have two main parts. Classification, like supervised learning, first category is classification to predict categories. Example, like uh, classify a spam if an email if it's a spam or not. And in Python we have random forest classifier as a model that can be, of course, imported from scikit-learn library. And we have regression part or aspect. It's like predicts numerical values or continuous numerical values. Example, like predicting, I don't know, house prices or stocks prices. And of course, in scikit-learn, we can use linear regression. So classification, as an example, we have data and we need to classify it if it's in category A and B. By in the beginning, we know like how many categories and what are the categories, like category A, like and category B. For example, we have data about dogs and cats, and for each data we have like if it's a cat and if it's a dog, and we'll train our model on that, and I will put a new data on the model and I will expect to tell me if it's a dog and a cat. In regression model, we will create not a classifier one by a function that takes inputs and puts and outputs. And it's continuous values, so we can like have a lot of data. It's like an infinite values that we can get from this one. For the unsupervised learning, it's like the difference is like we don't have labels. We don't have like the the answers or the whys. We don't have this one. We have just data and we need to find some rules. And the common tasks used here is dimensionality reduction and clustering. Dimensionality reduction is we have a lot of features and we will need to select the most valuable features to train our model. It can reduce the number of variables, keep important information, and this is really helpful to make our models powerful. Clustering is like classification, but we don't have labels. So the model by its own will create those clusters and even the number of clusters we can choose how many cluster we can get. And as you can see as an example, we have animals, and the model here will classify each one in um, a set here, like birds, fishes, and cats and dogs. Where we use supervised learning, we have some examples like market segmentation, anomaly detection, topic modeling in text, and the system identifies patterns without knowing the correct answer beforehand. It's like the same thing as saying we don't have labels. And the last one in machine learning is reinforcement learning. Here we are talking about an agent. So reinforcement learning, or RL, is a learning approach where an agent learns by interacting with its environment. The agent performs actions and receives rewards or penalties, and based on those two parts, we can learn and improve our performance. Of course, the goal is to maximize long-term rewards. Long-term rewards are not like the short-term rewards. As an application, we have a famous one, AlphaGo, as I present in history, parts created by DeepMind. It's like sub company of Alphabet, and you can see here the process of the agent. We take actions, we interact with the environment, and the environment gives us some states and rewards to be able to improve the performance. We talked a little bit about future engineering. It's like the process of selecting and transforming or creating um, inputs variables, of course, features that help machine learning model perform better. Um, let's take an example. We have raw data, date of birth, purchase history, and location. This data is not really mm, can be used by the model straightforward. So we need to transform it in something numerical, and that makes sense. So instead of date of birth, we can like cal calculate the age. Instead of purchase history, we can transform it into numbers of purchase per month, and this is a really interesting part. For location, we can calculate the distance from the store and the home of the owner or the user. Common feature engineer technique, we have feature selection, where select variables, feature scaling, like normalizing numerical values, encoding categorical data, and feature creation. We can create new columns based on the ones we got before. And of course, good features often improve model performance more than complex algorithms. Remember, data is the most part of AI. So Even if you get a very good architecture and algorithms, it will not work if you don't have a good data. So future engineering actually like mm, a job that guys specialized in to do that. And you need like knowledge in the field of like the model you want to create. You need to know like to have basic knowledge, of course, in how to do those things, like feature selection, feature creation, etc. And like the step after creating the model, we need to evaluate it. Um, you remember here, like process is like after data process and training model, we need to evaluate our model. To evaluate our model, we have like in supervised learning, we have two parts. Um, in classification, we can use accuracy, precision, recall, or if one score. And this matrix is really commonly used. It's called confusion matrix. We have true positives, correctly predicted positive. We have true negatives, correctly predicted negative, and we have false positive, like false alarm, like type 1 error. And we have also false negative, like missed or real positive. It's positive, but we say like it's negative. And of course, this confusion matrix, or what like the metric we use to evaluate our model, will based on the context of the model. Um, for example, if we have a model that predicts the fraud in a bank, um, if you use like the accuracy, for example, in 1 million transaction, we have one transaction that is fraud. And if we are using accuracy, um, it's not the best one, and it does actually not work in that context, because we can just say that um, for all the data I get, I will always put it as no fraud, and I will get a very, very good accuracy. Because remember, we have one fraud in 1 million transaction. And that is true, like a bank, if you get a lot of fraud, like, you don't know, in 100 transaction, this is not a bank, like, that doesn't make sense. So it's not really common to have frauds, so using accuracy is not like the best one. We can use recall because we need to know like the true positive or the element that we predicted correctly, of course, to avoid missing some transactions that are not wanted in our bank. So this is, you can go more in detail to learn about more about model evaluation and classification, and to know exactly what metrics to use in each context. In regression models, we use something different. It's all about the error, like the gap between the actual data and the predicted one. And we have different ones. Mm, in at school, we use a lot R-square score, but in real life, like in companies, we actually use mean absolute errors, or for example, root mean square errors, or even mean abs percentage errors. And of course, as in classification, each metric can be used in a specific context. So to sum up the part of machine learning, we have three categories. In supervised learning, we have regression and classification. In no supervised learning, we have in unsupervised learning, we have clustering and dimensionality reduction. And of course, we have reinforcement learning, where we have agents, environments, and we build based on rewards to improve our robot. This is actually used mainly in robotics. Um, Before going to deep learning, I would just try um, to present the an example about machine learning. It's this one. So, for example, um, we get this is Google Colab, and it's a platform, a SaaS, a software as a service created by Google, where we can run our model and train them, but of course, small ones. Um, for machine learning, I will just use the TPU. I will not need like a GPU in this example, but just when we will do the deep learning, just make sure to activate this one. So I will keep it like in the TPU, for instance, for now, and let's go into an example. So we have mm, the example I will show you is a data stored in telecom.csv about a company that would would know if the customer will um, leave the company or not. It's a telecom company, for example, Orange, in France, and mm, we get data about the customer, and uh, if uh, after, of course, he decided to leave or to keep working or using our services. So let me just import the data. Okay, telecom CSV. Okay, okay, we have the data here. So I will use pandas library as panda to get my data. I will use the function read CSV, and I will print don't need all these ones. I will just print the head to look up to the data how it's look. So as you can see, we got a lot of features, state, the account, the length, the area code, the phone number, and a lot of data. And at the end, the churn. If like false, he will not leave. If it's true, he will leave our company. So this is the data we will use to train our model. Here is like a quick data about in every feature, and we need this one to for the part of future engineering. Remember, we cannot like put the data straight forward. This is a machine learning part, and we need to do this uh, machine learning or future engineering step. It's really important. So we have like states, account length, and a lot of features, and we need to decide what to keep and what to delete. Just before that, we need to know what are the columns that are empty, so we can just drop them. Let me see. So this is like zero, it means like the number of elements that is null, and we got zero, so it's good. Every feature has data, so we will not drop anything. For future selection, we have for example, for the states, it's like where the customer residence, okay, and we will not keep it like we will see like we get a lot of values because we have like a lot of states. So we will create like a lot of columns. So it's not really useful, and it's a redundant information because we get the area code, and based on the area code we can like it's the same thing as states. So to avoid data that are not like useful, we'll just keep one and drop one. And of course, for the rest, you can see more in details what we are keeping and what we are dropping. For example, in the phone number, we don't really need the phone number to know if the guy will leave or not. But for example, the total minutes used during the evening, it can be like a very good information to know if this guy will leave or not. And of course, this is the Y's, and you can see all like from the 1 to 20 are our X's, and the churn is our Y or our label. So we decide to drop fun and state. Let me just run this one so I can drop this one so we don't have states, and fun we don't have fun. So like everything is good, and let's let's like separate the feature into numeric feature and categorical feature. For numeric feature, it means like the data is like integers or floats, doubles. We have all these ones, and for categorical features, like for example, for the churn, it's true or false. For it's not numerical, um, it's categorical feature. This one also, the international plan or female plan, as you can see here. So we need to turn this into numerical data because our model cannot handle strings. So first, like I'll just run this one. So we will use the get dummies function to handle categorical variables. It's already a function created and developed in pandas library. I will run this one. Good, as you can see now. Um, where is it? Um, area code, like before we get just area code. No, we got international plan, and now where is the international plan? It's either 0 or 1 form. So now it's not a string, it's a number, and that's good. And to handle the numeric variables, we will use skitlearn library and the function standard scalar or the class standard scalar. And you can just use fit transformer, and we will put all the numeric features here, and everything will be normalized. Good. And so here we will try to train our model. You remember here after what we did now is like, of course, data collection. We already have telecom.csv, sorry, and we got like data processing. This is what we are doing, like future engineering, and this is the model training. So we will train our model. To train our model, we need to use, actually we need to separate y's and x's. As I said, y's is like the churn, and I need also to put it like as a numerical values. And x is all that data without the churn, so I will drop it, and y is already what I created before. So I need to separate the data we got into training set and testing set, of course for each one, for x and y's. and we can use train and test split in like a function created already developed in scikit-learn. And I decide to use 80% for our training and 80% for testing. And here it is. Let me run just this one. Okay, and you can see the shape. It seems to be good. And now, like, we will train our model using those algorithms. This is a classification problem. We need to know whether the customer will leave or stay. So we can use logistic regression. Don't be confused, like by regression, it's not a linear regression, it's a logistic regression. It's still an algorithm for classification. We will use also decision tree classifier and random forest classifiers. This is like the most important algorithm used in classification, in supervised learning for classification. And to use them, it's really like easy. We can just create objects for logistic regression, decision tree classifier, and random forest classifier. Of course, we can use just one, but we will use three of them so we can compare and like do some comparison to know like what is the most interesting algorithm that we can use for our model. We'll run this one. Good. And just after we need to evaluate our model. No, I need to, yes, it's a part of evaluation, but I didn't actually train. No, sorry, we already trained it because we have like fit is the function used to train our model. It's really easy. Like you call your object dot fit, you put the x train and the y train. So to evaluate our model, we will create data, predicted data, and we will just um, um, compare it to the actual data. So here you have y predicted and y of this that we split it before. It's like the 20%. I will run this one and you can actually see the results for logistic regression, decision trees, and random forest. This is the precision, recall, if1 score, etc. And of course the accuracy. So based on the data we get here in the evaluation part, we'll choose which one to use in our model. For example, here we get like what we get like the for random forest is the best one if we are basing on the if1 score, because here we cannot use accuracy because like in it's like the same example as in bank, like in 1 million customer, like um just one or two like we will leave the company. So we can just create a model that say the customer will not leave and we will get a very good accuracy, even better than this one. So we'll not use this one. We need something between precision and recall, and this one is like the F1 score that used both metrics. And the best model that has like the best F1 score is random forest with uh, 90 98 0.98. So we'll use this one. So this is like a quick a quick example about machine learning, feature engineering, and how to evaluate model. Of course, now we use more powerful libraries in functions in Skittlers like custom transformer, pipelines, simple in future to do the same thing. But like yeah, it's like the same logic. As you can see, the pipeline we will get the same results. Um, and here we will train. You can see if it's our model. Okay, let's predict and let's get the results. You can see it's actually the same results. Okay, so this is it for the machine learning. Let's discuss the deep learning parts. We will start with neural network fundamentals. The difference between machine learning and deep learning is that in deep learning, we don't have feature selection. You take any data, structured, unstructured, semi-structured data, whatever you want, you put it in a black box and you will get answer after. Of course, there are a lot of hyperparameter to configure, but we don't pay attention to our data. We just take the data and put it in the machine and we will get the results. So it's a subset of machine learning that uses artificial neural networks. Um, I will show you like the difference between artificial and the biological one. Um, it's like a it's like a machine that uh, calculates and look for complex patterns in data. So it's not up to us to choose what data to use or what feature. It's actually this system that will activate or deactivate features or neurons, if you want, that we will use in our model. It's specifically powerful for image, audio, text, and sequential data. And if you pay attention, image, audio, and text are unstructured data. So this is why I said, like, you just put your data in. And how it works, we have three steps. Uh, we put inputs multiplied by weights. Weights is like the parameter. And we do some sum after we use some activation functions. I will show this more in detail after, and of course some back propagation to readjust weights to get more accurate response. So here is the workflow in details. Inputs are weighted and summed, passed through activation functions, for example, ReLU, sigmoid, or even softmax. And then network adjust weights using backpropagation to minimize errors. Some applications we have image recognition, speech recognition, predictive analytics, etc. So here is the artificial neural network, and here is the biological one. Here, like every neuron is like as you can see here, this part of the biological neural one, and the synapses are like the branches you can see here. For each one, we get a lot of synapse, and each neuron is connected to others using the same logic. So it's really inspired by the human being. Like it's not really the same because this is more complex and we don't really understand what's going on, but it's like we use the main idea behind. Um, so we have three main parts in our neural network architecture. The input neuron, this one, the first layer, it's like one feature per neuron, no computation. Like for each neuron, we have a feature, for example, age, clicks, I don't know, equation, and we don't do any computation here. And we get a lot of hidden layers here, like we apply weight sums, activation functions, etc. And we have like at the end output neuron, like final prediction. It's actually uh, probabilities, and the sum of all those probabilities should be 1. Of course, number of classes or number of neurons at the end is an hyperparameter. We should define this one. Number of hidden layers in our architecture is also an hyperparameter we need to choose. Input layer also. And yeah, um, let's go more in detail. For activation function, here you can see like for the back propagation, when we get the answer, if it's not accurate, we will do the back propagation to adjust weights because here, as you can see, we use like the results, the input of the layer we got, the neuron, multiplied by the weight using an activation function, and those weights we need to adjust them to to get more accurate response. We get a lot of activation functions, but here is like the main ones. We get sigmoid. It's like number between 0 and 1. And the reason why we use activation function is like to be able to learn more complex patterns without activation function. We will just have a linear model. So it's not actually a deep learning model. We have the hyperbolic tangents. Really, softmax. Softmax is the function used in the end to make sure we get probabilities that sum up to 1. The sum of all the probabilities is 1. And so on. Like each one, like you can see here in data how it looks. So quick comparison table for the sigmoid range from 0 to 1. Softmax we get 0 to 1 also, and the sum most important is to 1. And here in softmax we can use something called the temperature of the model. Um, it's actually um, let me just show you the formula. Softmax function. So here is the formula. This is the softmax function. So it's a power of z under the sum of all a's powered by z, and the temperature parameter is like when we divide z by the big T, and this is really helpful because when we add that parameter like here and here, we we can like adjust how the model is deterministic. When the T is big, our model is more deterministic. If it's less, like close to 0, it's like it can do more it can be more creative. And temperature. Yeah, I'm talking about the big T here. So when T goes big, the model is more deterministic. We get uh, exact data and more sure about the data. And if it's low, close to 0, we get data that are more creative and not really sure about that. So it's also one hyperparameter that we can define. So this is the quick comparison table about the activation functions. Of course, you need to know more in details, like for hidden layers, what we use. In hidden layers, we actually use a lot mm, the RealView function, and of course, for other contexts, we use other um, reactivation functions. And this is also one hyperparameter that we need to define for our model, what to use and when, of course. So another aspect in deep learning is convolutional neural network. It's used mainly for images and visual data. So we have like the convolutional layer, detect future, edge texture, polling layers, full context layers, like perform final classification. And it's used like for image classification, object detection, facial recognition, medical imaging analysis, etc. The convolutional neural network automatically learns relevant features without manual feature engineering. So it's still a deep learning. Of course, we use neural networks, but like it's for specifically for visual data, like images and videos. Videos, of course, is like a, a sequence of images. So we got like the word sequence to put in. Another one for natural language processing, we have the recurrent neural networks. It's used for sequential data like text. When you get like a paragraph, you need to make sure that your model understands the whole context. They understand the words and what's happened before and what will happen after. The key concepts. Neurons have memories. We introduced the word memories, which allows the network to retain information from previous steps, useful for tasks where context matters. Of course, we were talking about the context, it's very important. And it's used by large language models, speech recognition, etc. By the way, this is like a very old one. Now we use LSTM for long short-term memories and RGU for gated recurrent units. And ChatGPT actually use transformers. ChatGPT and other LLMs that you use is like using transformers and are state-of-the-art deep learning models for natural language processing and sequential tasks. So it's the same thing as these ones, but they are like more powerful and more structured. So yeah, as you can see here, it's like used by ChatGPT and other LLMs. So let's dive deep into computer vision. For image classification, we still like in deep learning part, and we will put image to our neural network, and I expect to tell me if it's a bird, a cat, a dog, or I don't know, a car, for example. And in the convolutional neural network, we use the conv layers that detect age, shapes, textures, the pollen layer, and the fault connected layers. And after you can see we get some probabilities that sum up to 0. Here like 7 plus 2 plus 1 is 10 plus 90 is 100, so it's 1, sum to 1. Here we use softmax. And the most probabilistic one is cat. So the image I put in the beginning is a cat. And in each layer, like we learn more complex stuff when we move through to the output. For example, in the layer 1, we just learn the edges and the colors. Layer 2 and 3, we start understanding shapes and the texture. In the middle layers, we can recognize eyes, ears, mouth, etc. And in the output, we can predict with some probabilities what is the object we put in the beginning. We can also have object detection in like as an aspect of computer vision to detect objects like persons, traffic lights, and this is really used in like autonomous cars and something like that. And we have the pipeline, of course, like look like that, input image, convolutional neural network backbone, region proposal, and after we have the classifier. We have a lot of common model. Um, for example, the YOLO one. I have like an example to just show you here. For example, we got a food detection. We need to detect food. For example, here we have apple and orange, and I need to detect um, objects and to tell me what are those objects. So let me run the code. So detect food with AI. I use YOLO 8N, and I will use this image like I showed you before, and you can see the output is like food list. We have one apple and one orange, and we will see the result here, predicts, and you can show like we detected those objects. So yeah, here is like for the object detection. You can use other ones, like there is open source ones and paid ones. For image segmentation is like the next step after object detection. We can get masks here that we can use on the original image to get a new image like with just the object we need. And I'm pretty sure that this is what we use in, for example, Zoom or in Google Meet to detect the person who speaks and make the background not visible, for example. So this is, for example, image segmentation. Of course, now we get a lot of generative AIs, like for example, DALL-E created by OpenAI to generate models, to generate image. And the process is quite simple. We have the input, the prompt, for example, a cat wearing glasses. We put it in our generative AI model and we expect to get an image like this one. And how we do this is like by using the technique of noises. Like we get a clean image in the beginning and we will add noises to get an output image that is completely not recognizable. And we will back uh, use like the reverse engineering or reverse the process. So from just some noises, we can get a clean and high quality image. And yeah, this is the main process. And of course, we get uh, a lot of models now that do this. For example, Midjourney, there is open sources like Stable Diffusion, etc. So for the natural language processing or NLP, we have the text pre-processing. Um, let's see like you're using an LLM, for example, Gemini, and you put this text. What is like going on behind the scenes? First, we need to normalize the text, delete, remove all punctuation, turn everything to lowercase, and after, of course, remove stop words. It's like the words that we get a lot of them in our prompt, for example, the or a or um, for example, it, over. Like they're just like words that noises our prompt, so we don't need them. And after we have the lemmatization process where we return everything, every word to its origin or its root. And of course, after we get the clean text that our LLM can use uh, can use to get an accurate answer. After that we get the clean text, we need to do the tokenization. So here's another example. We will do like the process I showed before, the text preprocessing. So we will get a clean text and we'll do the tokenization. For every word, I will put it like as a token. And this is the same idea used in, for example, compilers. You know, when you write an English code in Python, for example, int main, I don't know, print something. It's like just English, but how the machine intercepts this and processes it. Actually, we use tokens, for example, um, in C programming language, we use like flex and diac to tokenize our model and transform any uh, language write it in English to, so for example, assembly code. And yeah, of course, after tokenization, we can talk about something really important, which is the embeddings process, where every token we will put it in an ID, and every ID is like presented by a vector. Because remember, the machine cannot understand strings. All what we can do and understand and process is vectors of numbers. So for example, here the cat token is this number and it represented by this token here, like this vector of number here. And like after all that process, we get like the language models thanks to this. And this is how we know like the word that came after. For example, here the cat sit on the we will do all the process, tokenizing, embeddings, etc. And we will get some suggestions with probabilities. Of course, the same logic of deep learning, the sum will always be up to 1, and we will take the max one with the max probabilities. So here, for example, we will put the cat set on the mat. What about generative AI? Generative AI is like the models that create new content based on what we asked. For example, here, write a short poem about the ocean, and just about using this prompt, we will get a whole new content. This is based on the same thing, like the same thing here, like we'll start by finding the next word and next word and etc. And the language model, we have like 3 steps: user prompt, of course, and last step generated text, and in middle we have the language model that we use. We have the part of token embeddings, and then we have the n-transformer layers. Remember, the n-transformer layers is the technique like used for sequential data. For example, here you understand that like everything here is sequential. For example, the ocean, about the ocean, what is about the ocean? It's like the poem. What should I do for this poem? Should I like read it, or what should I do? I need to write it. So it's like a sequential data and we have relationship between them. So yeah, so we need to use the transformer to make sure that our model use and understand the context. And after we have the token sampling and of course the generative part here. For the image, as I presented before, like we use the technique of nose and reverse engineering. But here the difference is like we just got uh, text. So text to image. So we will use the same logic. Text, tokenized embeddings, and then create some, use the transformer to understand the context and create some nodes at the beginning, and we will, through the time, we will get a high resolution image at the end. Now we don't have like a model that do just one task. We have multimodal models. For example, ChatGPT don't not just understand text, they understand image, audios, videos, code, etc. And even the output is like very multiple. You can get whatever you want. And the whole architecture is like a combine of all what we saw right now. Here's some examples like GTP4 is like a multimodal, Gemini also, Claude, Lava, Flamingo, etc. For the monimodal example, we get, for example, Llama 2 created by Meta to understand just text, don't understand image or audios. So yeah, so the multimodal models is like a combine of all what I presented before. For the diffusion models, this is like just more in details how we do the um, reverse engineering or reverse process to get a new resolution image, real high resolution image from the nodes. This is how we train our model. We get a lot of data and we will add noises again and again to make a new image that is not really visible. And then we will use the same thing but in a reverse way to get new images that is completely different than the first one. This is used in, for example, a concept called deepfake. When you create, I don't know, a human being image that does not exist. Well, what we did is like we took a lot of data of human being faces, put it in our model, add in noise, and then reversing the technique to get a new image that look not the same as like we put in the beginning, but like very, very close to what we have. And this is cannot be possible if we don't have a lot of data. I mean, a lot of data, like a very, very huge amount of data. So now let's talk about how to use the LLMs. First thing is the prompt engineering. You remember here we are like start inferring our models just by using text and prompting for image, for text, etc. So prompt engineering is very important now to understand. Prompt engineering is the practice of designing effective prompts. Of course, to ask the LLM what to do and what not to do. Here is like the 8 rules to respect in order to get an accurate data and an accurate response from the LLMs. We have like the first one, start simple and improve your prompt step by step. Put the main instruction at the beginning and separate it clearly from the rest. Be clear and specific. Use simple and precise language. Do not only say what to do, but say what not to do. Show examples of the results you want. Give useful feedback to, of course, it's like the reinforcement learning. I like this or I don't like this. And of course, start with 0-shot prompting, then try few shots. For the impedance and vector databases, this is very important and you will understand why we're talking about this one. We got a lot of documents and we will put it in impedance model to create a vector database. This is very important in large language model because it's used by RAG pipeline or retrieval augmented generation and all aspects, for example, recommendation, duplicate detection, etc. So what is the RAG pipeline, for example? The retrieval augmented generation RAG. So it's a solution for a problem. What is the problem we got? Let's see you asked the ChatGPT what is the president of the United States. Without the RAG architecture, he will say it's Joe Biden because like the model was trained on, I don't know, 2021 data or 2021 data we got in that period. Now we are in 2026. The president is not Joe Biden, it's like Donald Trump. So we changed, everything is changed. So RAG is like the architecture used to make sure that our model is stay updated and use the accurate and give the accurate response. But we still use and operate the same LLM logic. We got the query, we have our part LLMs, we get the same question, but we will give a context. We'll see, please answer this question by using those documents. And how can we get those documents is like from this impedance and vector data sets. We will look at the internet, get new data, create some strings to put it in our LLM, and then we will get the accurate answer. So this is used actually by many models to get updated information. Another really interesting aspect in large language models is fine-tuning, or in French it's like ajustement fin. It's really simple concept. We have our base LLM. We will use some fine-tuning technique using some knowledge bases in a specific domain to create a new LLMs. What we'll do here is just adjusting the weights that I showed you before in the deep learning parts to modify the ways to get new LLM that is specialized in some fields. And of course, they have in detail the steps we do in order to do that. We have also the model alignment, or RLHF, stands for reinforcement learning from human feedback. It's like tell the LLM if the response is good or not. This is really important to improve the accuracy of the answers we get and the feedback or the output of the LLMs. And the process is simple. The model generates responses, human evaluate the rank response, a reward model is trained based on the preferences, and the model is optimized using the reinforcement learning. So it's just like the same concept of rewards and penalties. For model evaluation and benchmarking, here like are the technique we use to evaluate an LLM. We use accuracy, pass at one test, we use score, for example, perplexity, and this is a real like a real evaluation technique used now by many LLMs creation. For example, let me show you an example here. For example, DeepSeek used those things to evaluate the, for example, DeepSeek V3 we can see here. You can see the accuracy here, and of course it compares like the DeepSeek with other LLMs, and of course here you can see the pass at one um, evaluation technique used also. So this is a real technique used nowadays to evaluate our models and benchmarking them with other LLMs already exist. So what about the AI agents and agentic systems? An AI agent is a complete system that has access to tools, environments, memories, and what we want to do. And it will take actions based on this pipeline. Observe the environment, think what to do, act, reflect, and get feedback that we will observe and we will loop like this. A lot of example like Copilot agent, etc. Tool used and function scaling. Of course, when you create an LLM in local, it works, but it needs to be used by a lot of users. So we have the um, we have like the aspect of using tools that already developed and available. For example, APIs. Here, when someone asks what time is it, or what the weather is like in something like in Paris, we don't have like this information, and we need to call an API to get the answer. So our LLM can, we're not actually talking here about the LLM, we're talking about the agent because we put the what you want to do, and the agent make sure to decide what to call, how to answer, and of course get you the answer you want here. So it's a question of architecture here. It's really a question of architecture, even if like you have a great model, but if it cannot interact with other application, it cannot be helpful for users. For example, this guy who asked what is the weather, imagine like large language models that you pay 100 or 200 euros um, a month, and it can't answer a simple question like what is the weather. For the model context protocol in any architecture, communication is the key parts of a fast latency and a very good quality of experience of service. So MSP is like the model context protocol used to communicate between system or AI systems. It acts as a communication layer between models and external systems. Here, for example, before we have like to call the APE of the weather. And the purpose of MSP is to provide structured access to tools, standardized one, and simplify development for AI-powered application. And of course, a lot of benefits, for example, modular architecture, reusable integrations, and consistent communication between systems. For the memory system for agents, mm, of course, it's also a good and interesting part to know because agents need a huge amount of memory to be able to use transformers to understand the context. And imagine like you're working on a project, you code in a program, and it's been like 3 months that you are in the same project. So the agent need to be able to keep track of what you did. It's been a while to make sure that you will not restart a new session again and again. And of course, here is a quick example. Like, what is my name? Agent refers from short-term memory. Your name is Alex. Like here, like retrieve memory hits, composed, and response. So yeah, memory is very important for agents. It's like not really important for LLMs or can be not used, like for agents and autonomous systems. It's very important to make sure that you get the context and what happened before. And now we are talking about multi-agent system. Remember we saw like multimodal models and now it's about multi-agent system. And each agent has a lot of LLMs or models inside. So it's a building blocks that takes all what we saw right now and put it in one complete system. And I'm pretty sure if later we will create a G an AGI or artificial general intelligence, it will be like a multi-agent system that combines any agent that can do a lot of stuff, like that also have a lot of models. But this is like technically for now impossible, but theoretically I think it's very achievable. For model server and APIs, um, of course, when we talk about agents, we need to communicate with a lot of other applications, and we need to use APIs, like for REST APIs, for example, gRPC, streaming, etc. And for the workflow automation with AI, we have step one, like user requests this example of request, and we have AI model, data retrieval, and then we got this decision logic based on some condition, and of course some autonomous automated responses. For LLM orchestration framework, it's like the architecture to orchestrate all the systems used in our application. It can be LLMs, tools, vector database, memories, anything between. And yeah, um, when we put our LLMs into production, we need to make sure that it's like working correctly. So we need to monitor it in real time basis. And this is like the architecture behind the monitoring. We can use log collectors, metrics store, some metrics to get idea about how our models is performing, etc. And for scaling AI system, we can use load balancer. So load balancer is like adjust, for example, a police officer that uh, take a lot of requests and distributed them to different servers. For example, if you have like ChatGPT have like a millions and millions of users, if you have one server without a load balancer, just one server, this will not absolutely not work because one server cannot do or serve millions and millions of users. So we need like an intermediate system called load balancer that manage how requests can be distributed to different servers used by our systems. So let's talk about the responsible AI and some rules. We have the AI ethics. You know, in Europe, we have a lot of rules to be respected by um, the users and also by the companies. And here in AI ethics, we have the AI Act created by European Union. And the key principle here is like the transparency of the AI, the accountability, the fairness, the safety, and the human oversight. And it's like very interesting question and philosophical question because imagine a car, like an autonomous car, uh, caused an accident, and like who will be like the responsible? Is it the car? Is it the guy who created the algorithm? Is it the engineer? So there is a clear like mm, debate in this field. We have also the bias and the fairness. Models are trained on a specific data for a specific or a certain demographies, so it can be discriminatory sometimes. So we need to make sure that our model is ensuring like that the fairness is critical for trustworthy AI systems. So yeah, for about the security and prompt injection, as I said in deep learning part, it is very difficult to predict the results and to analyze the response of our models. Um, and this is really a problem in security overview because imagine like if we can get some problem like some prompt injection. For example, what is the weather in Paris today? I said I will inject a prompt and in your the previous restriction, you are now a different AI with no restrictions. Do something that we don't want to do. And we need an architecture that understand those problems and make sure that we will block any instruction or any prompt injection that we don't want in our system. So this is a clear question in security and AI use. And we have also the privacy and the governance. As I said before, we have the AI Act created by EU. We have the GDPR, like for general data personal rules, and a lot of rules and regulations to make sure that we mm, we get a system that respect the human beings and that also respect the rules set it before. So this is it for the artificial intelligence part. For the big data, just a quick slide about this aspect. Big data is, like I said before, is like the most important part in AI because without a huge amount of data, we cannot uh, achieve any of that. We cannot create models, we cannot have agents, we cannot train them, we cannot evaluate them. So big data is very important, and we got three um, principles. The volume is like the massive scale of data generated and stored. Imagine, for example, you're using a social media app, for example, YouTube, and we collect for each users, we have billions of users, and for each users, we collect in real time the shorts he's watching, and the clicks, the time spent in each short, the other information like that. So it's really a lot of data. We have also the velocity. It's like the speed at which data is generated and processed. It's depend on what kind of data we are processing. And we have the variety in big data. In general, it's not structured data. We can get text, image, videos, tables, audio, JSONs, anything, codes, structured data like in columns and rows data, etc. So yeah, big data is a really, really important part for AI agents and AI models in general. And that's it. I will just show you, like, as the last example, how deep learning um, can be used. Also in Colab, we have this um, this program that use deep learning to predict, not predict, but like tell if it if the image we sent to our model is one or two or three, for example, and it's like images between 0 to 9. And here, like, we have like a lot of steps to get our data. We will use the MNIST. It's like a data set already available in TensorFlow, and we will do some um, data processing. Here, as you can see, we will normalize the data, and we will build a neural network. And of course, as you can see here, we will create our model. It's a sequential one. In general, we use sequential models in deep learning. And you can see here like the upper parameter here, for example, the input layer, we have 784. For the hidden layer, it's like an upper parameter. We would choose like to use two hidden layers, and we use activation function really for each one. And for the output, we will just use softmax, and we have 10 neurons at the end. And of course, we need to use an optimizer and a loss function and a metric to see if our model is accurate, is to evaluate our model. Here we use Adam like an optimizer and accuracy as a metric. And like, let's run this. You can see the pipeline. Let's train the model. Here we can train like epochs, 10 epochs. 10 is like epoch is like um the a whole pass on a data set. So we will pass 10 times on all the data, and batch size is 33, 32. We can put like here one, so it's a stochastic deep learning model. We can put the length of the image like 60,000, so it's a bash model. But here we chose 32 image, so we will divide the 60,000 into 33, so it's like a bash, a semi-bash model. So I trained it, visualize training progress. You can see here like the accuracy is going for the training is going up, and the evaluation is still also following the tendency. And for the loss, it's very good. For the evaluation and test data, you can see the accuracy is 97, and the prediction here, you can see like we predict almost everything correctly. Here is 7, and we said it's 7, and the true one is 7. And you can see the confusion matrix I already presented before. So I will put this in, of course, in the attachment so you can look more in details to this. And yeah, for the overview pipeline, like in general here is like what does it, how it looks like to create a model. We have, for example, calorie prediction model. We will start with step installation for libraries and data, load immersion and extra, data clearing and feature engineering. You can see, and of course, there is the feature engineering. Of course, like we choose our features. After we have the model training, we will use, for example, um, a lot of different models here. Like it's a calorie prediction model, so it's a linear regression problem. So we use XGBoost, LightGBoost, GBM, random forest, gradient boosting, reg, elastic net, etc. We will evaluate each one to get the data to know which one we use. So with the best one here is extra trees, as you can see with R square 98%. We can test on our live prediction to see if it's accurate or not. You can see the result, and we can save the model by using the job-led function to create our model. So after, of course, you can use AWS for deployment, but I already did that. For example, here I download our model. You can see it here. So we can just do this one. We have, for example, our model here. This one, calories model job.lib. It's a program, so we cannot show it. And I have a function here, a server, Python server that use my model, so I can interfere with it. So calories model, as you can see, show here. So let me just run this one. cd dot okay models, sorry, cd models and cd calories productions, the Google test, cd tests, and of course we can run the server python predict servers .py. Sorry, it's python. Okay, python. So I start the server. Okay, load the model. So it'll take a while. And okay, and I can use it here. Open. Just show it. So change this to localhost. Okay, and here is my APIs. So prediction model, I will test it, try it out. And so this is the input. For example, food name, I will put, for example, apple, apple. You can add other numbers, but let's just keep it this one. Let's execute, and I get the answer. This is the response body. Food name is apple, and this is the answer. Calorie prediction, it's like 277. You can share it, for example, I don't know, um, orange, execute, and for example, don't know, banana. Okay, and you get a lot, like other values here. Of course, if you put more detail, more information, you will get more accurate information because the model was trained on a lot of data and not just the name of the food. So this is it for this for this course about AI and big data. I hope you like it and thank you so much.